So here's chapter 17, part 1. So in terms of electrophilic aromatic substitution, in benzene, although benzene's pi electrons are in the stable aromatic system, they're available to attack a strong electrophile to give a carbocation. So the pi electrons will attack an electrophile. This, once it attacks the electrophiles, this complex that it forms, the covalent complex, is called a sigma complex. And then once the sigma complex is formed, right, it's a carbocation that's stabilized, a base will come, deprotonate, and reform the aromatic ring, generating your substitution over here. So the mechanism of electrophilic aromatic substitution is as follows. First is electrons from your aromatic ring come, attack the electrophile, form a carbocation. That carbocation is resonance stabilized, so electrons can move around the ring as such to generate these three possible resonance structures of the sigma complex. After that, you have base in the system, deprotonate, reform the aromatic ring, now with the electrophile attached. In terms of bromination of benzene, we had seen in the previous chapter, although the mechanism wasn't given in detail, that if you just take Br2, this reaction doesn't happen. But when you take Br2 in the presence of catalyst, you have the electrophilic aromatic substitution leading to the bromobenzene and HBr. So in terms of the mechanism, you have Br2 in the presence of the catalyst. This Br will come and form a complex or an intermediate where you generate a slightly positive Br charge and Fe slightly negative charge. This is then becomes a stronger electrophile than Br2, right? So this is positively charged strong electrophile. And this FeBr, which is a catalyst, is a Lewis acid catalyst, which allows this complex to form, which allows the electrophilic aromatic substitution to happen. So then, if we look at this with the complex involved, after that complex formation, you have electrons attack that bromine, right? This quenching that positive charge, now generating the sigma complex again, where you have resonance stabilization, where the electrons move around. Remember to add your brackets and your double-headed arrow, and then your FeBr4 minus. FeBr4 minus will come and deprotonate, reforming the ring and generating the product. Important thing to note is that the three resonance forms of the sigma complex show positive charge on the three carbon atoms orthopara to the site of substitution. If we look at the energy diagram for bromination, here's your reactants. You have your first step, which is the attack from the electron ring to the Br from the complex, generating an intermediate, and then this is followed by formation of the product. That difference in energy is about negative 45 kilojoules per mole, and the transition state, the rate limiting transition state, is that first step. You can actually do chlorination of benzene. Chlorination happens in the presence of a catalyst. Instead of iron trichloride, use aluminum trichloride, and you can get substitution, electrophilic aromatic substitution, and generate the chlorinated product. You can do the same thing, and the mechanism is the same as the iron tribromide bromination, so I won't go in detail. You can do the same thing with iodine. In this case, you're going to use iodine in the presence of an acidic oxidizing agent such as nitric acid. This will generate an iodide cation. So if we look at this, nitric acid in the presence of iodine will generate the iodine cation, and that is what reacts with the benzene to generate the iodobenzene. So that, again, that mechanism is the same in terms of the rest of the mechanism of electrophilic aromatic substitution. Nitration of benzene. For nitration of benzene, you have nitric acid, and then that is used in the presence of sulfuric acid. The sulfuric acid acts as a catalyst, allowing the reaction to be faster at lower temperatures. And when you take these two together, the nitric acid and sulfuric acid react to form the electrophile of the reaction, which is nitronium ion, generating the nitrobenzene. So let's look at this mechanism in a little bit more detail. Here you have electrons from your nitric acid pluck off the protons from the sulfuric acid, generating complex shown here. Then you have electrons from your oxygen come down, kick off the water, generating the nitronium ion. And this nitronium ion is what's the reactive electrophile. Now if we take our benzene, electrons will go to the nitrogen, kick off electrons from that double bond to the oxygen, and now you have your adduct. Again, you have resonance stabilization where your electrons move around this ring in brackets and the double-headed arrow shown here. Three possible steps, or three possible resonance structure, and then over here you have the loss of a proton from the HSO4 minus, forming the nitrobenzene. You can take that nitrated benzene in the presence of zinc, tin, or iron in dilute acid, HCl. You can reduce that nitro group to NH2. So this is how you would take or add an NH2 group. It's through the process of nitration and then a reduction step, second reduction step over here. You can actually also sulfonate the benzene. You can take benzene in the presence of sulfur trioxide and acid. The acid you're going to use is sulfuric acid. So if you take a 7% mixture of sulfate and H2SO4, this is called fuming sulfuric acid, and the SO3H group is called sulfonic acid. So once you have the catalyst, then you can generate rings from your electron attack to generate benzene sulfonic acid. This is now in resonance, right, where you have electrons, right, go over here, that's one, and the electrons go over here to generate the adduct. If we look at sulfur trioxide is shown here, and you can see sulfur trioxide has various resonance forms, right, because you can have electrons from here go, or you can have movement of electrons. Where now you have these possible resonance structures. And as a result, it's a very strong electrophile. So now if we look at the mechanism of sulfonation, right, your electrons from your benzene come, kick, and electrons from your oxygen, your double bond go to the oxygen, forming your sigma complex. Again, these have resonance structures, which are not shown here, but three resonance structures we talked about in 2 slides ago. And then you have your HSO4 minus come in, deprotonate, form the resonance in the benzene. If you have a benzene sulfonic acid in the presence of water and acidic acid and heat, you can actually desulfonate. So the sulfonic group then gets removed and you regain your benzene. The mechanism for desulfonation is as such: your electrons now go to the protons from the acid, regenerating your resonance delocalized complex. And now your oxygen, so there again there's going to be three possibilities, only of one is only shown here. Then your electrons from your oxygen goes to the sulfur, reforming your benzene and then generating sulfuric acid. Nitration, right? So in terms of nitration, if you start off with, instead of a benzene, a toluene, the same reaction, so the mechanism is the same, or in the sense of electrophilic aromatic substitution. However, you get three different forms, possible forms of nitration. Ortho nitration, in which you form ortho-toluene or orthonitrotoluene. Meta-nitration, and you form meta-nitrotoluene, and then para-nitrotoluene. So what's interesting is that in the nitration of toluene reacts 25 times faster than benzene. The methyl group is an activator. Product mix contains mostly the ortho group, as you can say, 60%, and para, but very little of the meta. So let's look at ortho and para substitution. If we look at the first step, right, attack of the nitro, then it generates three possible resonance structures. So here you have the ortho position, then you have electrons move, so that now you have it, this was tertiary, now it's now secondary, this moves again, and over here. If it's para attack will form on the para position, right? It forms the secondary carbocation, and then when we look at resonance, here you can move, and then you have a tertiary, which is most favorable, and then from tertiary that moves again to form another secondary. So if we look at this, the ortho and para have two possible tertiary carbocation structures that are favorable. As a result, you have ortho and para being favored over the meta attack. If we look at the energy diagram, if we have benzene and toluene in the presence of the nitrate, the highest in energy in terms of formation of the nitro adduct is the benzene, then it's followed by meta, then followed by ortho and para. If we look at the meta attack, right, so if we attacked at meta, here's your reaction. You have a tertiary, this moves again, and no matter how much it moves, you always have each time a secondary carbocation being formed in the resonance structures. As a result, it's not as favored as the ortho and para. In terms of alkyl group stabilization, so if we take this ethylbenzene and react it with bromine in the presence of the catalyst here, you can have the three possibilities: ortho, meta, and para. And again, ortho and para are favored, right? 30 and 62 over meta. So if we look at this, alkyl groups are essentially activating substituents on the ortho and para. So they're called ortho and para directors. This effect is called inductive effect because the alkyl rings can donate electron density to the ring through the sigma bond, making them more active. So in terms of anisole undergoes nitration about 10,000 times faster than benzene and about 400 times faster than toluene. And so this this results in ortho and para preference, and the oxygen is strongly electronegative, but donates electrons from the oxygen into the ring system, stabilizing the transition state and the sigma complex. So if we look at substituents with non-bonding electrons, such as this methoxy group, first step is the nitration and ortho attack. In the subsequent steps, you can have your electrons from your oxygen come down to form this product over here, or you could have your electrons move in that ring, so for moving over here to generate this product over here. Again, electrons moving again from here to this position to generate this charge, the charge moving around. Again, if you have ortho attack, you form your nitrate. Now you can have electrons from the ring moving that positive charge, and then once you get to this place, you can have electrons from your oxygen come and participate, and this generates this really stable form. Then you can go back to the ring and move the electrons around once again so that you generate this possible one. So the resonance stabilization is provided by a pi bond between that OCH3 substituent and the ring. If we do meta attack, you have generated this, and then you have all the possible ring structures, electrons moving around in the system, and all of them show that the methoxy do not stabilize the sigma complex when it's meta-substituted. Bromination. So if we have anisole and we react with bromine in the presence of water, so you don't need to use a catalyst now. You can just take 3 equivalents of bromine and water, and it'll generate this 2,4,6-tribromoanisole in 100%. So if we look at aniline, in the presence of 3 equivalents of bromine and water and sodium bicarbonate, to neutralize the HBr that's formed, you generate in 100% 2,4,6-tribromoaniline. So if we look at activators, we can see that oxygen is the strongest activator, actually an alkoxy group, followed by anilines, followed by OHs, which are phenols, followed by ORs, which are phenyl esters, or phenyl esters, sorry, and anilids, right? Amide group is being attacked, and then just alkyl. So this is something that you should know. Activators and deactivators. So if the substituent on a ring is electron donating, the ortho and para positions are activated. So here's when you have a donator, such as the alkyl group. These two, this is ortho, and then para, those are activated. But if you have an electron withdrawing group, W, the groups on, the ortho and para positions, these are deactivated, so then you have preference at the meta position. So if we look now at nitrobenzene, these nitro group are electron withdrawing groups in the presence, and if you're doing nitration, so now in this case, your electrophilic substitutions reactions for nitrobenzenes are 10,000 times slower than for benzene, and then your product is predominantly the meta instead of ortho and para. So if we look at why is this so, first step, right, of this is your nitrate group already, it's electron withdrawing, you have attack on the electrophile, and now when that happens, you have these charges that are adjacent to one another, and this is especially unstable. So, so you want your electrons to move around and have that instability kind of be dissolved away by separating the charge. And so here you have separation of charge, so you're at your meta position, and also you can then move your electrons, and also again you have another meta position. So the nitro group is a deactivating group when we're considering resonance forms, and that has this formal positive charge, and you want to minimize the positive charge being next to one another. So ortho and para addition will create these really unstable intermediates, and as a result, this ortho substitution does not less likely occur. So for meta substitution, if you have your attack, now you have your possible combinations where you have your now positive charge residing here. It's still very separate from the nitro group already. Electrons move around, electrons move around. And in no case in these three possible resonance structures do you see that positive charge on adjacent atoms. So if we look at the energy diagram for electrophilic aromatic substitution in the case of benzene and nitrobenzene, you have nitrobenzene, really highest in energies are the ortho and para because of that charge being close to one another. And then meta is favored, right? And then benzene is actually more favored than the meta substitution. Deactivators and meta-directors. Most electron withdrawing groups are deactivators and meta-directors. Atom attached to the aromatic ring has a positive or partial positive charge. Electron density is withdrawn inductively along the sigma bond, so the ring has less electron density than benzene, and thus it will be slower to react. If we look at ortho attack of acetophenone, so here's acetophenone, attack on the ortho position. Now here your charges, right? So this is partially positive charge. Here's a positive charge. This is unfavorable. And then if you through resonance, you're going to have the other positive charge moving around. So in the ortho and para substitution of acetophenone, which is an electron withdrawing group, one of the carbon atoms bearing the positive charge is the carbon attached to that partial positive carbonyl charge. Since those charges repel, right, like in the previous case with the nitrate group, this close proximity of the two positive charges is really unstable. If we do meta attack, right, and we have our charges move, again, you're going to have the charge move from here to here to here. In all cases, you don't have that charge repulsion, and so this is going to be stable, at least more stable than the other. So if we look at a list of deactivators, we talked about nitro groups, right? It's a deactivator, and you saw that positive charge existing in the resonance form. Sulfonic acids are actually also deactivating, and you can see that in the resonance form, the presence of a positive charge on the sulfur. Cyano, right, has a positive charge on the C of the cyano. Ketone or aldehyde, again, positive charge on C. Esters, positive charge on C over here. And then quaternary ammonium, which is already positively charged, right, will also serve as a deactivator. Halogen. So if we have a halogen and we want to react it with nitric acid and sulfuric acid, you're going to have ortho and para being preferred over meta. So halogens are deactivators since they react slower than benzene, but even though they're deactivators, they are ortho and para directors. So why? It does this through inductive effects. So halogens are deactivating because they're electronegative, right? Electronegative meaning partially negative. And so what they're going to do is they're going to withdraw electron density, as you can see over here, from the ring along this sigma bond, CX bond. So it becomes less electron rich. Now, halogens are ortho and para directors, because if we look at these examples, if we have ortho attack, right, then you can have electrons from your bromine come in, right, and stabilize that, and that is the most stable, right? And you can have the other forms. So this is a shorthand version of the resonance structures, but actually in an exam I'd like you to show all the possible resonance forms with the double-headed arrows. If we do para attack, right, para attack will generate a bromonium ion in which this is the most stable one, right? And then you can have electrons move, and you can have the electrons stabilize in resonance at these positions. But if you have meta attack, right, you can only have that positive charge move around in which the bromine doesn't participate in the stabilization of the ring. So if we look at the energy diagram, the most or the least stable is the meta attack on the chloro, followed by ortho and para substitution, and then benzene, which is more stable. So in terms of summary of directing effects, you have activating groups such as pi donors, sigma donors, and they will prefer the ortho and para. Then you have the deactivating groups. Halogens, right, are electron withdrawing to some extent, and then carbonyls, and these other groups are meta-directing because they're bona fide electron withdrawing groups. So remember which substituents are activating and which are deactivating. Activators in general are ortho-para-directing, deactivators are meta-directing, except for the halogens. So this ends part 1 of this chapter 17.